Hi guys, welcome to Computation in C. I'm Josh Kilpatrick. This is a series of lectures, or a course if you will, about computing, programming, the history of computers, and also the theory of computation. We're going to be looking at the C language, but we're here now in our third episode, and we're going to continue our history lesson a little bit just to situate ourselves in history and where this computer revolution came from. So in the last episode, we took ourselves through sort of a lot of the major computational inventions that happened up to the 20th century, up to the 1900s. And now the Industrial Revolutions broke out. We have air flight, we have the telephone, we have the telegraph, and we're turning into the 20th century, and wow, we get smacked in the face with World War I, where some of these new inventions become really important for the way warfare gets waged. And in particular, the air flight and creating things like bombs becomes an important kind of part of how the world is thinking about the technology of war. Well, as World War I is settling down, we begin the story, kind of pick up the story again with a famous mathematician whose name was Alan Turing. I'll show you a picture. Alan Turing was working on his PhD thesis at King's College in Cambridge when in 1936 he penned a really famous paper from a mathematical perspective that actually built an abstract foundation for thinking about computers and computing. And we're going to spend some time today understanding and learning a little bit about what he invented, what he envisioned, and how it has sort of been a stepping stone that's led us to where we are today. So Alan Turing invented a concept called the Turing Machine. And I'm looking for a good photo of it here. It's not really a real thing. It's a conceptual idea, but if you were gonna try to envision it, it might have looked something like what I'm showing you here on the screen on the left. So kind of hold that in your brain, and I'm going to describe to you in an abstract way, like Alan did in his paper, what was a Turing machine and why was he even proposing it. So let's get started here. 1936. Turing is beginning his working on his paper, and he comes up with this idea that he could represent mechanical computation in the following way. Imagine we had one big, long, infinite paper tape that, we had an unlimited supply of this paper tape. It went in both directions forever. Okay? And on this tape, we can record symbols. Like the tape has little boxes, kind of like a movie film, where we can record a symbol. By a symbol, I mean something like a letter, like, A, B, C, or a number, 1, 2, 0. We can record symbols onto the tape. So that's part one of his machine. Number two, he says, and now imagine that I have a device, a reading head, he called it, that could read what is on the tape and could write onto the tape. So this is theoretical. He can't really build this necessarily. He's just saying, imagine something like this existed. This could be built. And then there is a controller. And we're going to just call this M for the Turing machine. And this controller has a couple different features. First of all, it has a state and a set of states that it can be in. So it currently, at every moment, it has some sort of state. And we'll talk in a minute, what does that mean? Number two, it has a set of instructions and we'll talk in a minute about what does this set of instructions look like, okay? And the third aspect of it is it has access to this reader and it can read what is on the tape, okay? And it can move the tape. So it can move left and or it can move right or it can not move at all. Okay? So a machine or a Turing machine is an infinite tape where you can record symbols, a read-write device that allows you to read what's on the tape and write to the tape, and then lastly, some sort of envisioned abstract machine that has a state, a set of instructions, and it can move itself left and right, up and down the tape. Okay, so you're thinking, wow, this is pretty abstract. Why is he writing about this theoretical device? He goes on in his paper to say, with this simple machine, he can prove that any problem that could be solved by a computer, you could envision a machine like this that would solve that problem. And we're going to prove this to ourselves here in just a minute. Any machine that can be built for computation, anything that could ever be done by any machine like that can be represented by this machine. Why was he even caring about this? Well, he wanted to demonstrate mathematically that there are certain kinds of problems, certain kinds of mathematical problems, certain kinds of thought problems that computers simply cannot solve. There exists no such computer that could solve this problem. And so he was really working in the field of math and numbers, but he was trying to demonstrate there is a limit to what can be done with mechanical computation, with a algorithmic computation. Now that's a little brainy. Don't stress too much if that doesn't make sense. The point is, he wasn't really thinking about computers the way we think about them today. However, he did go on in his life to build a lot of devices very similar to his papers, and he became very famous for cracking the codes of the Germans during World War II. You might have heard of a movie about him called The Imitation Game, where it tells the story of this famous German encoding device called the Enigma. Let's pull up the Enigma just for fun here and show you what I'm talking about. So this is kind of what an Enigma machine looked like. It was some sort of thing that kind of looked like a typewriter, and inside of it, it had different mechanical disks and devices, and what it was an encoding machine. You could type a message, and it would encode the message in a really, garbled up way, and then another Enigma machine you could type the message back in, and it would reverse the coding. So this allowed the Germans during World War II to encode messages on paper, and pass it back and forth, and the enemy couldn't read it. Well, this guy, Alan Turing, figures out how to build a machine that will crack this code, and it has a lot to do with all of his theoretical work in computation. But again, when he invented, or when he penned the idea of this Turing machine, he wasn't necessarily thinking about computers or thinking about building a computer the way we're going to see later, that happens later in the 20th century. Okay, so he was trying to prove a theory about computation. So let's just goof around a little bit with this idea of a Turing machine, just to get ourselves comfortable with the idea of what is going on. How would you even use a machine like this? So let's imagine for a minute that we want to add together two numbers, okay? And I'm going to do something really, really, really simple, and I'm going to say, okay, here's our tape. The way we're going to set the machine up is we're going to say, we're going to indicate a number on the tape in the following way. If I want to represent the number 3, okay, I'm going to put a 1 symbol in the first 3 slots on the tape. So this represents 3, okay? And then I'm going to add a slot on the tape where there's a 0, there's nothing. And then I'm going to add on the other side of the 0 the next number that I want to represent. Let's say it's the number 4. So I'm going to represent that with 4 consecutive 1s on the tape, okay? And Alan Turing would have said, okay, given a tape like this, how could I create a machine that would be able to add these two numbers, and in the end, what we want the result to be is that the machine will stop, it will finish, and it will have on the tape, in this case, 3 plus 4 is 7, so it would have 7 1s in a row, 7, and the machine would stop and would be pointing at the answer. So what instructions and states do I have to give this machine? How do I program it to do this? Well, if you just think about this in a really, really simple way, and you're going to think I'm playing a trick on you here, if I want to add together two numbers that are represented in this format, all I need to do is remove this 0 and scooch all these numbers over. And I'm going to end up with what I want, okay? So let's see if we can envision how to do this. So my machine's going to start up and it's going to see that it's looking at a 1 on the tape. And what I'm going to ask the machine to do is, hey, when you start up, if you're looking at a 1 on the tape, you're going to write a 0 and you're going to move left. And then you're going to keep moving left until you encounter a 0. When you encounter the 0, you are going to move, you're going to write a 1, and then you're going to return back to the starting place. And at that point, we will have changed the tape so that it looks like this. So let's think about how do we do this. So the way to envision the instructions of a Turing machine are like so. We have a set of states. Okay, that we're gonna describe the states coming down this way, and then I have a set of symbols that can be on the tape. And we only have two symbols on our tape, a 1 and a 0. So at any given moment, the tape can have a 0, we can be looking at a 0, or we can be looking at a 1. Okay? So what we're going to do is we're going to say, all right, the machine is going to start up in a state that I'm going to call Q1. It starts up in Q1. I just made that up. That's the state of the machine. And the machine's going to have several states. We'll see in a minute. So the way the machine is going to be defined is we're going to say, okay, start the machine. when you're in the state of Q, okay, Q1, if you're looking at a 0, well, that's an invalid machine. It's not supposed to ever start pointing at a 0. So I'm just going to say here that we will change the state to what we're going to call an error state. So I'm going to call it Q error, and we're just going to halt. That's it. We define Q error as a final state. So if it enters that state, the machine's dead, something was wrong, I wasn't pointing to a 1 when the machine started, that's an invalid state for the machine. Okay? Stay with me. This is going to make more sense the further we go. Let's say the machine was pointing at a 1. We've already decided what we want to do. I said it earlier. We're going to write a 0 onto the tape. Write a 0 onto the tape. Okay. We're going to transition to a new state that we're going to call Q2. And finally, we're going to move the head to the right. Okay, so we've entered state Q2, we've moved the head to the right. The head is now, this has become a 0. I'm just gonna say that's become a 0, and now my head is pointing right here, okay? So what happens next? Let's define what we want to do if we're in state Q2. If we're in state Q2 and we have reached a 0, okay, that means, okay, what was on the tape before was a 1 and a 0. And so that means the first number is a 1, all right? So when I encounter the 0, I am going to write a 1. I'm going to transition into state Q3. Okay. And I'm going to move to the left. Now, if I don't encounter a 0, if I encounter a 1, all right, all I'm going to do is I'm not going to write anything. I'm going to remain in state Q2, and I'm going to move to the left. So I'm going to keep moving left as long as I see 1s. But when I see a 0, I'm going to... Sorry, I just completely said that the wrong way. Let me correct myself. I'm going to move right. I'm going to move right. So as long as I keep seeing 1s, I'm going to keep moving the head to the right, moving the head to the right. But as soon as I see a 0, I'm going to move to a new state called Q3, and I'm going to move back left. So let's see what this looks like in state 2 as I continue with my tape. So right now I'm pointing at a 1. I'm in the state Q2. And when I'm in the state Q2, it says if I see a 1, all I do is stay in state Q2 and I move to the right. So here I am. I'm moving to the right. Now I'm pointing here. All right, run it again. Oh, I'm looking at a 1 again. Move to the right. All right, now something different happens. I'm not looking at a 1. I'm looking at a 0. And in the state of Q2, if I hit a 0, I've instructed the machine, when you hit a 0, you should change that 0 to a 1 and then move left. All right, so now I'm pointing right here. All right, so now what do I need to do? Well, I need to get the machine back to the very first 1. That's our agreement, that we're going to leave the machine in a state like this, where it's pointing at the beginning of the answer, the addition of the two numbers. Okay? So, in state Q3, here's what I'm going to say. If you run into a 0, if you're back here, okay, I'm not going to write anything. I'm going to move to the state Q4, and I'm going to move to the right. If I see a 1, I'm going to remain in the state Q3, and I'm going to move I'm sorry. I've gotten myself confused, as you do. Give me 1 second. So we're in the state of Q3. When we see a 0, we are going to move to the right and move to Q4. If we see a 1, we're just going to keep moving to the left. So we're going to stay in Q3 and we're going to move to the left. So we're going to keep moving the head over, until we get back to this 0. When we get to the 0, we're going to move right, and then we're going to go into state Q4. So let me show you. Q4. All right. So in its current state, I'm pointing at the 1, and I'm in the state Q3. It says if you're pointing at 1 and you're in the state Q3, move to the left. I'm going to move to the left. All right. I'm still in state Q3. What am I pointing at? I'm pointing at a 1. What does it say? Move to the left. All right. Move to the left again. Now, remember, we've updated our tape so that there's a 0 here. That happened at the very beginning. So now I'm in state Q3. I'm pointing at a 0. Okay. I'm going to move right and go into state Q4. So now I'm going to move back here. Okay. And we describe the machine. We say this is a done or finished state. Okay? And we have one more state we need to define, and that is the state QE, which means error. This is also a done or finished state. Okay? So in this simple way, I've written a table of instructions that describe how to take two numbers that are written on the tape in what's called a unary format. So if I want to do the number 3, I have to have 3 ones. If I want to do the number 4, I got to have 4 ones. 1, 2, 3, 4. And if I want to add those two numbers together, a basic addition operation, all I got to do is sort of smash the two numbers together. I just got to push them together. And I just described how to write a Turing machine that will do that. These are the instructions that will accomplish that by moving the machine over until it finds a 0, changing the 0 to a 1, and then moving back to the start of the first one. I end up with a machine that's pointing at a tape that looks like this. And we say, this Turing machine will take any two numbers, add them together, and then go back to the start of the result. It'll sit at the front of the result, and the machine will stop. So Turing was envisioning you could do a lot more complex things than this with a Turing machine. He goes on in his paper to kind of build the proof. In fact, you could do anything that could possibly be computed with a computer, with an algorithm, can be described as one of these very simple machines. And he goes on to use this to demonstrate that a certain mathematical class of problems exists that could never be solved by a computer. I think that's really fascinating, that even before a computer existed, this dude, Alan Turing, in 1936, penned a paper that said, here's a model you could use to envision a computation, any computation, and using that model, I can prove to you there are problems that just could not be solved by a computer. There must exist problems that can't be solved by a computer. It's a little too technical to explain what do those problems that can't be solved by a computer look like. I think you'd need a university course to really fully grasp that. But what I really wanted to hone in on today is long before a computer existed, in the early decades of the 20th century, a man named Alan Turing kind of wrote a model for modern day computer science and how to think about computation. Really fascinating stuff. It won't be until another decade later before engineers build what is the first real general purpose programmable computer. And that computer was called ENIAC, and it was built in 1945. So a couple other things that I want to bring to your attention. So in 1936, Alan Turing pins his conceptual Turing machine. By 1945, we have the first real computer that's been built. But it was built using these electrical devices called vacuum tubes. These vacuum tubes were kind of large devices. Let me show you what they looked like. This is, by the way, a picture of some women working on this early ENIAC computer. ENIAC is what it was called. They were working on this gigantic device, and it was so big because inside of it, we were using these devices called vacuum tubes. They look like what you're seeing here at the top of your screen, these little bulbous tubes. These had been invented in 1904 as sort of a part of dealing with some different electrical signals. But what property they had is that they could hold a state. They could either be in an on state or an off state. We're going to talk a little bit more in a minute about why that on-off state was so important. But here we have a computer being built by 1945, roughly 10 years after Alan Turing writes this paper. We're using the components that we have available to us at the time, the vacuum tube, to store a state, on or off. We're going to talk in a minute a bit more about this idea of states being represented as on or off. But let's continue the story. So after the ENIAC computer is built in 1945, the next big thing that happens in computers is that in 1947, as a part of Bell Laboratories, that's like the Bell phone company, the telephone company, a couple engineers there, 3 different engineers, discovered or invented transistors from a new kind of material that had been discovered called semiconductors. So let me show you a transistor. They look kind of like this. You know, this is sort of what a modern transistor would look like. And symbolically, we represent them like this, like I'm showing you here on the screen. There are 3 pins on a transistor, a collector, an emitter, and a base. And the idea of this little small device inside it has some very special materials that conduct electricity under certain conditions, and under other conditions, they don't conduct electricity. So you can turn them on and they'll conduct electricity, or you could turn them off and they won't conduct electricity. And all you need to really understand is that the transistor was an invention that came along just before the 50s began, 1947, and the transistor opens the doorway for us to start creating computers that are much smaller. So when the first computers were built, it was inconceivable that they would be able to be placed on a desk or in somebody's home. They were gigantic because we didn't have a electrical device that could store a state that was small. But as of 1947, we get this with the transistor. So let's continue now. The next big thing that happens is in 1960. What's called the integrated circuit is invented. And the integrated circuit was just a way to put an electrical circuit, a connection between a bunch of different transistors onto one chip. So instead of having a bunch of individual components that you had to wire together, the integrated circuit, a manufacturing process, and materials were created to build a really complicated electronic circuit made of millions of transistors and put them into a little small package. So the invention of the transistor happens in the 1960s, and then about 17 years later, in 1977, the first commercially available computers hit the market. The Apple computer hits the market, a special computer called the Tandy from Radio Shack. Radio Shack used to make computers, and another type of computer called the Commodore. I mentioned in an earlier video that a Commodore VIC-20 was the first computer that my family ever owned when I was a child. We got it in 1981. So what I've traced here for you is from the turn of the century and the ending of World War I, we get the mathematical proofs and theories of Alan Turing that kind of formed a mathematical foundation for computer science. World War II hits. Turing becomes ultimately famous for helping crack the codes of the Germans, Enigma Machine. The war comes to an end in 1945, and right along that same time, the first real general-purpose computer, the ENIAC, is getting built. It is made of vacuum tubes. It's gigantic. By 1947, the transistor gets discovered and invented at Bell Labs. Now we can miniaturize the vacuum tube. By 1960, the integrated circuit. Now we can have a bunch of transistors all together at once in a small package. And by 1977, the first commercial computers hit the market. It's a pretty fascinating story how we got from nothing to the advent of modern computers right around the end of the 70s. So let me back up and spend a few more minutes on a topic that's going to become very important as we get into our next lecture, which is going to be on how computers represent numbers and letters. How do computers do this? So I mentioned to you before that one of the things that we were having to do with the early computers is figure out a way to use electricity to store a state. Now, we can all envision how to store a state with a physical device like a switch. Let me switch over here. You can envision how using a mechanical switch, I can have two states. It can be on or it can be off, okay? Just using this as a symbol for you. It's a switch, it can be on, it can be off. But how do we do something like that with just electricity in a circuit? How do I store a value, or how do I store a state using electricity? Well, we would say something like either electricity is present or it is not present. The switch is on or it's off because electricity is present or it is not present. The first way that modern computers, or the first way that these early computers were being built, was using vacuum tubes. As we said, those were really big. Later, we come up with a transistor, smaller, but we're still just basically representing something as either on or it's off. It's on or it's off. So why is this so important? Well, okay, so we've basically electricity, modern use of electricity dates back to about 1831 when Michael Faraday invented his dynamo. So here we are about 100 years later when Turing is writing his paper, and we're still kind of figuring out all the things that electricity can do for us, and we've come up with this idea with these transistors that we can store a state of on or off with electricity in a physical device. So here's how I want you to think about this. We're going to talk about how to represent a number if you just have transistors. So let's say I put 3 transistors side by side, and I'm going to represent them as squares. And I can turn them on or I can turn them off. How could I use these 3 transistors to represent a number? Okay, first of all, we could say that all the transistors are off, and we could say this represents 0, the number 0. Okay? Now, what else could I do with the transistors? Well, one thing I could do that's pretty clear is I could say, well, I could leave the first 2 transistors off, but turn the third one on. Sorry, I didn't get that colored in very well. And I could say, okay, when my transistors look like this, I'm going to say that represents the number 1. Okay? How else could I organize the transistors? I could say, well, let's turn the first one back off, but turn this one on. So now I could say, we're going to say that represents the number 2. And then how else could I organize the transistors? Well, I could turn both of these first ones on, right? And we'd say, that represents 3. Okay, so I've represented 0, 1, 2, and 3. Well, how much further can I go? How much further can I go? What more can I do with these transistors? Well, over here to this side, I'm going to show you another possibility. What if I turn on this first transistor, and then I just repeat all of the states of the second 2 transistors? So it's going to look like this. The first one's on, these 2 are off. The first one's on, the middle one's off, last one's on. Looks just like this row, except I've got the first transistor on. Next one I'm going to say, okay, turn on the first transistor, turn on the second transistor, and the third transistor is off. And the final option here is turn all 3 of those suckers on. Now, in this little simple example, using just 3 transistors, I've showed you how we could say, okay, these 3 transistors represent a 0, a 1, a 2, a 3. Over here we could say that's a 4, that's a 5, that's a 6, and that's a 7. Okay? So what literally is happening inside a computer is inside of the memory of the computer, you could conceptually think of it as a bank of transistors. They're typically 32 or 64 transistors wide. This is microscopic, of course. But in the computer, I can among those 36 or 64 transistors, I can have each one either on or off. And I can start to represent numbers in this way in memory. So in our next session, or in our next lecture, we're going to talk a little bit more about the properties of these numbers and how to do operations on these numbers, how to add them, subtract them, multiply them, etc. We're going to talk a little bit about that. And then we're going to talk about how did people use these ideas to represent letters of the alphabet. So, how can I store in memory the name Josh, my name, Josh? I've showed you how I could store a number, but how could I store Josh? So in our next lecture, in our next talk, we're going to go over what are the properties of numbers that are represented in this way, and how could I represent letters. And it's going to be really an interesting final sort of foundational lecture before we start opening up our compiler and writing some programs. So I know that's what you're waiting for. We're getting there, but I want you to have some of these fundamental concepts and some of the history of computing in mind as we start to dig into how do I write programs for computers. So see you next time. Thanks for joining.